Hey everybody, thanks for joining us. This is the iMAPS New England student session, which is something we've been doing for a few years now, and it's very near and dear to our hearts. Jim Eakin and Dipak Sengupta have been instrumental in putting this on this year and in years past. And I just have a couple of quick announcements to make for the chapter before we get started here. The main announcements really are for our 48th Symposium and Expo, which will be May 3rd, 2022 at the Boxborough Regency Hotel in Boxborough, Massachusetts. And we are now accepting abstracts. If you are interested in submitting an abstract for review, the email address is on your screen right there, imapsne-abstracts@imapsne.org. We look forward to seeing as many of those as possible. And as a reminder, we do have student poster sessions, and I think we'll probably have a student session, a university session as well. So, you know, that's open to all. We'd love to have some submissions for that. Also, our exhibitor registration is open too. Right now, it's the best time to sign up for as an exhibitor. You get your best rate. We don't ask for payment up front. We'll bill you beginning of the year, but log in now and register for your booth space. With that said, I'm going to pass the microphone over to Jim, and he's going to take it away from there. Thanks, Jim.
Sounds good. Thanks, Matt. For those of you who do not know me, my name is Jim Eakin. I'm staff at WPI supporting some of the photonics initiatives. First of all, I'd like to thank the iMAPS New England Leadership Committee, as well as the student presenters and the special guests for giving your time tonight to showcase the work and research that you're a part of. Again, I'd like to emphasize that the main part of this Zoom tonight is to really showcase the breadth and depth of student talent across Massachusetts and New England in a format that we can get as many students in front of the iMAPS community in a fairly concise event rather than kind of going on for 3 and 4 hours. So the goal for tonight is to have students essentially present an elevator pitch or just a snippet of what their work is and what they're working on and how it's relevant to the iMAPS community. So what we'll be doing is I'll be kind of driving the slide deck from my side for the student presenters. Each of the students will have, roughly 3 minutes. I will raise my hand at the 2.5 minute mark to kind of guide them that they should start winding down, just to be cognizant of everybody's time. So we have roughly 12 student presenters, so that'll carry us through about the first hour, and then after we get through the student presenters, we'll go out into different breakout rooms and have the opportunity to mingle and network and have the ability to ask more technical questions within the networking session. And Matt, I believe we're probably going to do 2 10-minute breakout rooms.
Yeah, that sounds about right, Jim.
So we're going to hack through this. So we're kind of learning as we go, but please be patient as we try something new. So again, what I will do is I'll start off that, we encourage students to present and submit abstracts and participate in the spring events. Next year is more of a traditional poster session, but for now, this is a quick snippet of their work. So the first speaker we have on the docket is Professor Busnina from Northeastern University. Professor Busnina, do you want to share your screen and take it over?
Yes. Yes. Let me see here. Okay.
And is 7 minutes okay from your side?
Yes, I mean, for me, it's okay. Yes.
Okay.
So, I'm gonna try to focus my talk about. So we do high rate printing. Let's see. So I'm going to talk about high throughput nano and micro scale printing of interconnects and electronics, and I'm going to talk mostly about wafer level packaging applications. And so 2 of our students will be talking about a slightly different application. But I'm going to try to give you a big overview of what we do. So this came out of NSF Nanoscale Science and Engineering Center. And typically it's about printing using, without using etching, it's additive without using etching or using vacuum, for example. So if you look at it, right now we have the microscale, low cost and low throughput printing, which is inkjet, screen, and others. And it's limited in the sense of the alignment capabilities. It's limited in terms of scale. It's limited in terms of throughput, especially with the inkjet. And on the other side, we have the nanoscale, of course, high cost and high throughput conventional semiconductor.
Professor?
Yes.
I don't think we can see the slides you're showing.
See, hold on. Let me see if I can do it again. Can you see now?
Yes. Yes.
Sorry about that.
So maximize that one. Yeah.
Okay. So let me start over. Sorry about this. So basically, it's a high throughput nano and microscale printing. And on one side, we have the microscale, low cost and low throughput, especially with inkjet printing, typical printing that people use. And then on the right side, we have the high scale conventional fabrication. And then there's nothing in the middle that's additive, that's nanoscale, low cost, and high throughput. And that's what we focus on. And so imagine if you can take your design and materials in one end, in one machine, and have the electronics come out of the other end on the same day or in just 2-3 hours. And imagine if any small and mid-sized company can actually make their own electronics on the same day, as long as they have that design. And could the cost be 10 to 100 times less than conventional fabrication? And actually this technology already exists and has been demonstrated at the micro and nanoscale at Northeastern University. This was funded by National Science Foundation, DOD, and industry. And so some of the features, you can print any material on any surface, any material that you can suspend in a liquid. You can do that. It's all solution-based. Feature size has been demonstrated down to about 20 nanometers. It is 10 to 100 times faster than current technology. It's about 1,000 times reduction in material use. It's all additive. It's about 1,000 times faster than inkjet or 3D printing. And you can print crystalline metal or semiconducting structures. And so the whole thing is one tool that you can see right here. So how does it work? So it works by, so if you look at inkjet, for example, we have one droplet that has a lot of particles, and you basically move the inkjet, and the droplet decides what your feature size is. So your feature size is limited by the size of the droplet. And also you rely on mechanical accuracy because the jet is moving back and forth, for example. And most of the inkjet is limited right now to metals and to organics. What we do is very different. We don't actually do droplets. We control individual particles using either electrophoresis or using convective assembly or using fast fluidic assembly or the electrophoretic assembly. And we deal with particles down to 3 nanometers in size. You see this picture where we have 10 nanometer quantum dots. These are cadmium selenide that are assembled in a structure, a square structure. So this way you can print 1,000 times faster and 1,000 times smaller features than inkjet. And one layer is printed in 1 minute on a 4-inch substrate, for example. So there's no accuracy, there is no mechanical accuracy issues within the same layer. These are some of the examples that we have. And here you see that these are 5 micron silver lines with variable spacing. We have copper interconnect. Here you have printed crystalline gold and silver. We can print interconnect in submicron. These are actually 50 nanometers in size. You can print even magnetic material if you want to for magnetic applications. You can also, this is a wafer. We have 37,000 transistors on this wafer. And you can print, each layer takes 1 minute on the wafer. So when you're printing, either you're printing RDL or you're printing devices, whether it's passive components or active components, you need to align. And the alignment basically is very important. And there's a lot of trend now to basically get the alignment down to micro scale, sub 5, sub 2 micron scale. So here you see an aligned gate on an aligned gap between source and drain that goes down to 2 microns. So the 2 micron, these are 4 layers, as you can see here, and the gate is exactly on top of that. This is basically a printed pattern of silver. So basically, we were trying to measure the resistivity for the printed patterns. So we printed about 3,000 patterns that look like this, and we measured them. And the resistivity in this case was about half of the bulk value. And this was all done, like I said, 1 minute per wafer. And here you see the uniformity. For example, this is a 50 micron wide line and 1 micron thick, and you can see it's very, very uniform. This is devices. What allows you to print RDL with active or passive components at the same time, monolithically. And this is a transistor that gets you about 10 to the 6 on-off ratio after annealing. What about the lines? How small can you get? So this is a touch display, 2 micron line grid. This is a touch display application. And you can actually go down to 300 nanometer lines, as you can see here. These are 300 nanometer lines with very small edge roughness. So in the end, basically, you have one tool that you can do all that in one machine, one tool, one equipment, like you see here. And you can use a variety of materials. Any material you can suspend in liquid, you can print on any substrate. It's all physical chemistry, no reaction, no chemicals, no chemical reaction. And minimum feature size 20 nanometers. The tool actually can go submicron. 20 nanometer needs a more advanced capability, high throughput, and very low cost. And so actually this technology has been licensed. There's a spin out of Northeastern, has been licensed by NanoOps. And NanoOps basically has 2 tools, one that prints on flexible substrates and one prints on other substrates, rigid substrates such as sapphire, silicon, glass, quartz, or any other types of substrates. So I'll stop here and see if you have any questions. I'll stop sharing now.
That looks wonderful. Thank you very much for doing this. I'm sure we're going to have more questions in the breakout room.
Okay.
The next presenter that I will bring up is Jonah Yu. Jonah is a 3rd-year undergraduate at Northeastern. And if you allow me, I will share my screen and Jonah will take it from here. Oh, I have Tara first. I'm sorry. Jonah, we've got you up first. Go ahead.
Hey guys, I'm Jonah. I'm a 3rd-year undergraduate electrical engineer at Northeastern, working with Professor Busnena and Tara, who you'll meet next. And the purpose of my project is to additively print basic electronic components on rigid and flexible substrates with the following benefits: high resolution and high throughput, like the professor discussed. It's far better than inkjet or screen printing, and the additive nature allows you to conserve a ton of material and save a lot of resources. Reduce fabrication costs because a lot of the expensive etching and high vacuum processes are cut out of our methods. And alternatives to thermal annealing and our functionalization and fluidic assembly allows us to use a variety of substrates, whether they're thermally sensitive or not. Our alternatives are really useful for that. So we focused on resistors, capacitors, and transistors as our 3 components. For the resistors, we used a carbon black-based ink, and figure 1 shows the fluidic assembly on functionalized silicon dioxide. These samples were flash annealed, and then figure 2 shows the current versus voltage curve. It's very linear and ohmic, showing resistive behavior. And so for the capacitors, we used 2 dielectric inks, silica and aluminum dioxide. Figure 3 shows the confocal analysis of 2 silver electrodes with the silica assembled between these electrodes. And these reach capacitance measurements of about 80 to 100 picofarads, whereas the aluminum oxide on a rigid substrate was about 320 nanofarads. UV annealing was used for aluminum oxide to allow little thermal damage to the flexible substrate and allow easy assembly onto this flexible substrate that might be more thermally sensitive. For the transistors, we use single wall carbon nanotubes and oxide ink suspensions. Figure 4 shows this these transistors assembled on PET flexible substrate. There's no annealing required for these transistors, so that allows for easy assembly onto the flexible substrate. And in terms of performance for the transistors, the on-off ratio is about 10 to the power of 4, so it's getting to a desired value a little bit higher. In terms of future work, we would like to optimize our capacitor and resistive inks and processes for more flexible substrates, and also improve upon this somewhat average on-off ratio for the transistors.
Great, thank you very much. Oops. All right, let me move back. I'm failing here on my slide deck. All right. Our next presenter is Tara Hayek, also a third-year undergraduate at Northeastern. Tara, take it away.
Thank you. Hi, everyone. I'm Tara Hayek. I'm a third-year undergraduate student at Northeastern University, working under the guidance of Professor Ahmed Busnaina and postdoc researcher Anthony Childress. Our work is mostly based on the directed assembly and characterization of 5 semiconductors, and especially the directed assembly of 3 5 semiconductor nanoparticles, which are gallium arsenide and indium phosphide, using a polymer-free template. In our case, we're using ball-milled gallium arsenide and indium phosphide nanoparticles in order to make our work more scalable. So we're also working on the creation of nanoparticle inks using gallium arsenide and indium phosphide, as well as their assembly to circuit elements, the annealing process, and electrical characterization in the future. So why this is important? So this is important because this method can yield semiconductor circuit elements at the submicron scales on flexible or rigid substrates. So as you can see in figure 1, we can see indium phosphide channels with gold contacts for future electrical characterization. This figure also shows a thin film transistor setup or configuration for the 4-probe measurement. And each gold contact is a square of 100 micrometers in length. So in figure 2, we can see the crystallinity of indium phosphide nanoparticles as a function of the annealing temperature and time. And as you can see too, as the annealing time increases, the sintering of indium phosphide nanoparticle gets better since we're getting bigger crystals as the annealing time increases. And finally, in figure 3, we can see the indium phosphide clover with gold contacts for also electrical characterization. And each clover is 200 micrometers in length. And we're using this shape in particular because we're using the clover for the Hall effect in the van der Pol configuration. So that's mostly my work. Yeah, thank you.
Great, thank you very much, Tara. All right, if you give me, I don't know, 5 to 6 minutes, I'll kind of give you a quick overview of where we are within the WPI LEAP facility. I'd first of all like to acknowledge the rest of the team on this project, including Doug Petke, Ellen Pacholi, Bogdan Vernescu, and then our partners at Quinsigamond Community College, including Jacob Longacre, Adrienne Linnell, and Kathy Wrench. I would also like to acknowledge that this would not have been possible without having funding and support through the Mass Tech Collaborative M2I2 program and through the leadership of AIM Photonics and AIM Academy. So there's been a lot of people that have kind of helped get us to this point, and it would not have been possible without anybody else on the team. For those of you who are not familiar with the LEAP network, it was really an opportunity to support some of the Manufacturing USA initiatives In fact, WPI is a part of roughly 11 of the 14 manufacturing USA institutes. The one that I'll be focusing on today is mostly related to the AIM Photonics initiative, which is developing the next generation photonic devices and photonic integrated circuits. So the LEAP facility is really an on-road to this next generation kind of workforce development and a lot of the research initiatives around advanced manufacturing. And then within the LEAP network, there are a number of other Massachusetts-based schools that have their own LEAP facilities, including MIT, Stonehill College, Bridgewater State, Western New England University with Springfield Technical Community College. So the main emphasis of the WPI LEAP facility is really to promote the education and workforce development, as well as providing open access to an instrumentation facility to support some of the prototyping and research and development needs around photonics, photonic devices, with an emphasis of sensing and sensing technologies. To give a flavor of kind of the where we are as kind of a regional snapshot, the WPI facility is located in Gateway Park in Worcester, roughly a half mile off campus. And then within the Gateway Park facility, there are a number of other WPI research institutes, as well as being in close proximity to the Massachusetts Biomedical Initiative, which has just become a hotbed of startup companies focused around therapeutics and biotechnology. And again, there's a nice collaboration and partnership that we're starting to kind of kick off between WPI and MBI as kind of an on-road to support some of the research and instrumentation needs. And then 3 miles up the road is Quinsigamond Community College. For those of you that have kind of been following, our timeline over the last 4 years, I mean, this is really probably a 4-year snapshot of where we've been from the original kind of blueprints and drawings of building out the space to doing a soft opening on the main campus in the basement of Olin Hall with our nano 3D printer, to where we started to move in late 2019. And I would also like to say we were able to continue our entire research operation over most of the pandemic in the last year and a half, which really allowed us to bring equipment in, train students safely, and to really kind of be open for business. So this just kind of gives you a snapshot of where we've been. And then the next slides will give you an overview of the equipment and capabilities and the types of engagements that we have within the LEAP facility. So the LEAP facility is roughly 12,000 square feet of space. It's a combination of collaboration space, faculty offices, faculty research labs, and the core LEAP facility. The core LEAP facility includes 3 distinct labs. 2 are heavily on the AIM Photonics side. So it's the nano micro prototyping fabrication. So it's a class 10,000 clean room that houses our nano 3D printer, able to do submicron features both laterally and vertically as an additive manufacturing process. We also have more of the traditional photolithography equipment in contact, non-contact, optical profilometers as well. A lot of the equipment that we have in the metrology and test and characterization labs includes, the highly specialized photonic integrated circuit probe stations, as well as electrical probe stations capable of probing for 5G and 6G applications, as well as a number of kind of technology agnostic metrology tools, including 3D microscopy, spectroscopy, and a large format AFM capable of interrogating, up to a 200 millimeter wafer. And then on the prototyping side or the functionalization side, this is really a collaboration between the LEAP facility with photonics and the NextFlex facility and engagement with flexible hybrid electronics, geared more towards characterizing flexible hybrid electronics, printed circuits, as well as a lot of the system level testing for that type of work. This also provides a nice overview of where we've been. I'll kind of present a caveat that the snapshot was taken pre-COVID, so it's always a little alarming to see, a lot of people in a crowded space without a mask. So it just kind of shows how far we've come in the last year and a half. But this was an event, some of you I hope can remember that we hosted a joint iMAPS New England Optical Society of America event on campus, and really gave students the opportunity to kind of pitch their work and talk about their experiences. And it was a way to kind of provide a tickler for the soft opening that hasn't really come yet, but it still will in the near future. But again, we've hosted, and we look forward to hosting networking events in the future going forward. And I'll close by just really emphasizing that we're hoping through this initiative to create a sandbox that combines both the research, the education, and the workforce development through the instrumentation facility, through project-based learning, and really presenting students from the associates all the way up to PhD level work that are gearing up to work in industry. And we're really proud of our collaborations and partners at QCC that are really a stronghold in the workforce development work as well, and their photonics program. And then in addition to that, there's the typical engagements of, we're happy to make the connections to faculty and faculty sponsored research, and present the students for co-ops and internships, as well as develop more of a strategic partnership with companies and the greater central Massachusetts ecosystem. So that is LEAP in a nutshell. So thank you very much. Our next presenter is Tuna Tafan, a PhD student at WPI.
Hello, everyone. Today I'll present to you my work on a fluorescent thin film-based miniaturized transcutaneous carbon dioxide monitor. So there are millions of people suffer from respiratory disorders such as COPD and asthma. And after a successful medical treatment in the hospitals, the discharge of this critical population should be supported by continuous monitoring of the respiration action. And the arterial partial pressure of carbon dioxide is an important measure for the effectiveness of respiration. However, current monitors are either invasive or can be used only in clinical settings. And with this work, we present a miniaturized non-invasive transcutaneous carbon dioxide monitor, which can measure the transcutaneous carbon dioxide level of patients in a continuous manner and in a home care setting. And the prototype is envisioned as a wearable monitor, which will measure the carbon dioxide diffusing from the skin. It's also called the transcutaneous carbon dioxide. And we are using a carbon dioxide sensitive fluorescent thin film to assess the carbon dioxide level. Our benchtop experiment the results showed that the fluorescence intensity of the thin film is inversely proportional to the carbon dioxide concentration. And the prototype can measure carbon dioxide levels within the clinically relevant range for healthy humans, which is from 35 to 45 millimeter mercury. And that initial result shows that the viability of a future wearable carbon dioxide monitor, which can replace the contemporary bulky bedside monitors that are widely used today in the clinics. So the current monitor that we designed is a PCB design. It's composed of discrete off-the-shelf components. So I'm currently working on the chip design of the system, which will further miniaturize the monitor and make it more suitable for a wearable application. Also, we are looking for future collaborators for the manufacturing of the biocompatible and flexible packaging of the wearable electronics. That's all from me.
Great, thank you very much, Tuna. Our next speaker is Alex Chalisa, also from WPI.
Okay, thank you, Jim. Hello, everyone. I would like to introduce our work in miniaturized continuum robots for in-office minimal invasive laryngology procedures. So we create a new steerable laser fiber system that can be integrated into the current medical workflow to treat patients with larynx diseases in office-based procedures, like the one you can see on the top left image here. So physicians pass an endoscope through the patient's nose all the way down to the larynx, and then deploys a rigid laser fiber through the endoscope working channel. The camera and the lights embedded into the endoscope provide visualization of the larynx tissue, and then with the fiber, they apply laser pulses to remove the tumor, similar to what you can see on the bottom left image. So, however, if the tumor is placed at an unfavorable location, like below the edge of the vocal folds, these kind of laser fibers cannot easily be aimed at those locations due to this rigidity. To attempt this, we attempt to tackle this limitation by developing a scaled-down distal tendon actuated bending mechanism. This mechanism is a steerable probe made of a nitinol tube of 1.1 millimeters in outer diameter, with asymmetric rectangular notches along its body to provide deflection in one plane. So nitinol is a super elastic alloy that, in contrast to other alloys, has the property to recover its original shape after suffering any deformation process. We manufacture these millimetric notches using a laser cut process to create a series of 10 consecutive notches of 340 microns. Also using different manufacturing methodologies like high resolution 3D printer or CNC machining, we fabricated and tested a miniaturized end cap to hold in place the tendon, to actuate the steerable probe, and to hold the laser fiber too. Finally, to integrate the steerable probe in the medical workflow, we develop a motorized actuation unit and a control panel to provide 3 degrees of freedom to the steerable probe. The 3 degrees of freedom are translation, rotation, and bending. These units are mounted on top of the endoscope, as one you can see in the central figure. And physician can hold the endoscope and operate the steerable fiber similar to how they currently do, and continue using just one hand to perform the surgery. In preliminary simulation tests, we increase in average the reachable tissue in the larynx by 32%, and in the near future, we plan to perform ex vivo experiment on pink larynxes. Thank you.
Thank you, Alex. Our next speaker is Professor Benson Chen from Binghamton University. I will stop sharing, and Professor Chen, would you be interested in sharing your screen then?
Yeah, let me start it up. Can everyone see the screen?
Yes.
All right, so I'm filling in for Dr. S.P. Park. He's the director for the Integrated Electronics Engineering Center. My name is Benson Chen. I'm the associate director. I'm going to go through quickly what IEC is. It's a New York State Center for Advanced Technology. So basically, we're funded by New York State. And really, our goal is to look at research to help companies, with the electronics needs, be it materials, be it structures. We do a lot of work on failure analysis, understanding why the electronics fail. We also have facilities to do reliability testing, whether it's cellular thermal cycling, temperature, humidity, HASS, etc. We also have full shock and reliability capability. So to understand why something fails is the only way you can figure out how to make it better. So we also do a lot of work on research focus is heavily into heterogeneous integration, power electronics, flexible hybrid electronics, a lot of additive work, as well as a new task that was just started about 2 years ago, looking at artificial intelligence and Industry 4.0 for electronics manufacturing. And so what we actually have is a full SMT line that is integrated from the printer to the reflow, and we have capabilities of measuring all the parameters from step to step, and we can actually do automated adjustments for each machine. So that way, from the time you put a board into the beginning to the time you get the reflow, after reflow, you can actually say if there's something wrong, it can actually make adjustments back to the screen printer or the pick and place tool, or even during reflow, if you can adjust the temperature profile that you can set into the tool. So that's really the goal. We actually finished the first stage of that, which is to the screen printer to the AOI tool, the solder paste inspection tool, and that's actually up and running and actually is being used by industry today. Very small staff, basically, all experience from industry. Actually, most of the people that's on the screen came from IBM at one point or another. We have industrial members such as ADI, analog devices, ASE, which is the largest semiconductor manufacturing company in the world, based out of Taiwan. We have BAE, we have Corning, GE, IBM. So big companies, they're actually working with us for not just research, but also directed, research where they're saying, what can you do for, specific topics? So, for instance, IBM is looking at a lot of the low temp solders. So we're doing work on electron migration studies, failure mechanisms with low temp solders, understanding, the sensitivities of each of the joints. We're looking at helping with understanding warpage predictions. So if you look at the substrates, a lot of packages that are being developed today, even if you look at the packages on the cell phone, they're getting bigger and bigger. But if you look at high performance computing, I think this year they're already at 100 millimeters with many, many dies. So they see that going to 150 and beyond. So you think and look at multiple dies, large substrate, how do you attach it to your next assembly? You're still governed by JEDEC, which is 8 mils max coplanarity, and try to keep that substrate to a manageable, warpage. That's what we're helping ASC as well as IBM on understanding what can be done with the substrates, the underfill material, the different types of interconnects that you're going to have on it. So again, try to figure out what can be done to make that package more reliable, easier to assemble. If you have to use a lot of tools, that's going to take a lot of time. That's not manufacturable. That's not, it doesn't make sense for economics. As part of the center, we also have pool research projects. These are projects that are actually funded by the IEC. We have mentor companies that are attached to each one of them, but they're very diverse. So, first one that we show on the screen is femtosecond laser micromachining. We're actually developing a process where you use a femtosecond laser, and you can actually write waveguides in a piece of glass. So Corning is sponsoring it because they supply a lot of glass. IBM is actually thinking about using that to try to look at silicon photonics. You can write that, and you can actually change, by using lasers, you actually change local industrial refraction within the glass to create these channels. We have work on AC fast chargers for aircraft. We have extending the work on in-business-based solders for electron migrations. We're looking at the liquid anodes for lithium-ion batteries. So again, very diverse topics. These are all one-year terms. Mostly they're going to be funding grad students and basically for materials. So, a lot of work that we do, all these companies are looking at, possible uses, or they actually would be guiding those kind of processes. So this is just a quick chart on the SML, which is Smart Electronics Manufacturing Line. This is the line that we have that is a fully functioning SMT line for building prototypes, but we're using this for looking at the Industry 4.0 initiatives. We also provide prototyping services for small and startup companies. By using the line, we actually use that type of service to actually train the students on the running of the tools, as well as we use the data that we get from the prototyping to build into the AI system to actually increase the database that we can use for more components, different pitches, different solder temperatures, etc. we host a annual electronics packaging symposium. We just finished the 32nd year of it. And I think Dipak as well as David Salmons was actually a part of this, or part of the attendees. We had a great turnout. We had, basically 762 registrations. We had, it was amazing, how many people actually registered. And with this being a virtual, we still were able to get over 550 people actually attended at during the 2 days that we had this thing. So very good event. Topics that were of interest was the DoD interest in advanced packaging integration. We had 6 speakers from the DoD, each giving their needs for what they would like to see for electronics. And we had a good talk about the ERI, which is the initiative to try to get industry back. The electronics industry back into the U.S. So basically, we are an organization that will help, be it research, be it for manufacturing, be it for the company's needs, looking at failure analysis, looking at different materials, also looking at modeling and simulation. So if you need electronics, or if you want us to help you understand electronics, that's what we're here for. So that's all I got.
Thank you very much, Professor Chen. All right, our next set of speakers are all from Binghamton University, so I will go back to sharing my screen and introduce the next speaker. Speaker is Yang Lai from Binghamton University.
Hello, everyone. Can you hear me? So I'm Yang Lai. I'm the first year PhD student in SUNY Binghamton, and I'm working in the Professor SB Park group. So as you can see the title of my study, so this is about the reflow soldering process. I provide an approach to get the best solution of the reflow recipe. There are several heating zones in the reflow oven, as you can see the figure here. So the recipe here is the preset temperature of each zone. So when we are going to reflow a new developed PCB assembly with varied sizes of component on it, some are big, some are small. So the solder joints under the components with thermal mass differential go through different thermal profiles in the reflow process. So a good reflow recipe is to let the thermal profile stay within the proper range with the process window. So this is the key to form a defect-free solder joint in thermal perspective. So in this study, I built up a system coupling the CFD model with the machine learning model. So the result from the physics model is used to train the machine learning model. And to evaluate the result using the parameters such as peak temperature, ramp rate, and the time above liquidus. So we can extract the best reflow recipe within 2 seconds. So you can see the system bring us the convenience and the efficiency. I cannot say it's accurate enough to take the place of conventional field measurement, such as we use the profiling board, but at least it gives us a good reference to start with and beneficial in adjusting process of reflow oven settings. So next step, I will put both the CFD model and the machine learning model into one compact package. So if you don't have the knowledge of the CFD or machine learning, you can still get the benefits. So mostly this is my study. Thank you.
Thank you very much. Our next speaker is Pencheng Ying, a PhD student also at Binghamton University.
Hello, everyone. This is Pencheng Ying, and this is my second year in Professor Park's group. This work's title is Shaping Container Design Optimization for Shock Impact. So electronic products suffer from shock, vibration, and drum impact during shaping or or unused, which will cause electronics products failure like criterion, solder joint failure. So in this work, the job test experiment result of RAM modulus shipping container shows that the modulus is located in the tree of the job test, which could cause the potential damage in the interconnection. So therefore, in this work, we use the SSL to find the root cause, and the simulation results of the original model is matching with experiment result qualitatively. And also we design 4 improved models step by step for this container by combining different shock absorbing structures like corrugated structure and also the stiffener ribs. So, and also there are 5 drop directions for each improved model. As a result, you can see that in the table, the fourth improved model can reduce over 74% deformation as well as the impact energy for each drop direction, which means the decreasing the energy transmitted to the interconnection of the electronic components. From the result, we can observe that the stiffened ribs have a great effect on the side and bond drop, and the clasp structures which looks like the click structure is necessary for the shipping container, and also the corrugated structures only plays a very small role in decreasing the deformation if there is no such kind of click structure. So that's all for this presentation.
Great, thank you very much. Our next speaker is Ki Pan, a PhD student in his final year at Binghamton.
Hello, everyone. The topic of my this study is investigation of copper and glass deformation in through glass via during thermocycling. So as we know, nowadays, glass has been demonstrated as an alternative material to silicon interposer during manufacturing because of the outstanding mechanical and electrical advantages of glass. However, the CTE mismatch between the copper TGVs and glass substrate can cause a lot of thermomechanical reliability issues, including cracking in glass substrate, copper protrusion, and the delamination. Therefore, it is very important for us to quantitatively study the in-plane and out-of-plane deformation, strain and stress induced by the thermal mismatch at high temperatures during thermocycling or annealing process. So to achieve microscale measurement capability, for this TGV reliability testing, we developed a 2D DSC system integrated with thermal chamber to measure the in-plane displacement and strain stress of the glass substrate during thermocycling. So as you can see on the top schematic in our slides, you can see this is the testing system of their 2D DSC system and their screen technique. And in the meantime, their copper protrusion is another issue for the reliability of the TGV samples. So we use the white light profilometry to measure the in situ protrusion of the copper TGVs during thermocycling. So in summary, with the in-plane and out-of-plane in situ measurement results, we can actually have a better understanding about the thermal and mechanical reliability of glass interposer during thermal cycling and annealing processes. And these results can be utilized to improve the design parameters of glass interposer, such as their diameter and the pitches of their copper TGVs and their mechanical properties of their glass substrate. So that's all. Thank you.
Thank you, Ki. Our next speaker is Jinbo Yang, also a PhD student at Binghamton University.
Okay. Hi, I'm Jinbo. I'm the third year PhD student in the Professor Park's group. And For this study, our test vehicle has a generic structure of 2.5D package, and thermal interface material were placed between the die surface and the heat sink. And 14 heaters and 21 thermal sensors were built up in the thermal test die, like showing in the picture. And as cycles goes on, and team degradation behavior will show up, like pump up on the voiding issue. As a result, the junction temperature will increase after the degradation happened. So for this study, we choose the different team material to evaluate the team behavior. The Shin-Etsu 7762 and Honeywell PTM 7900 are used as our test material. So for the result, we choose the sensor 31 as our critical point to show the team behavior, because sensor 31 was near a real hotspot, represent the worst case. From the temperature plot, for the temperature circle, we run 3 times for the thermal grades, 5 times for the thermal grades, and 2 times for the phase changing material. From the temperature plot, we can find the phase changing material shows very stable behavior. But for the grades, thermal grades, as the cycles go on, the grades located at the hotspot region start degradation. Pump out issue was found, and as a result, the temperature shows a marked increase. For the power cycling, we run 2 for the thermal grades and make the 3 runs for the phase changing material. For the power cycling, a thermal grades shows pretty stable behavior, but for the phase changing material, one of its runs shows the significant increasing, and the local degradation was observed. So in summary, the phase changing material has better performance in thermal cycle test, but the grades shows more stable in the power cycling test, and the degradation was found in the local hotspot. So the phase changing materials perform better when the thermal loading is uniform, but the thermal grade shows a better performance and reliability during the non-normal thermal loading. And so for this work, next step is to build a FEA mode and to try to investigate the reason of why this happened. Thank you.
Thank you, Jinbo. Our next speaker is Zhang Wong Ha, a PhD student at Binghamton University. Zhang Wong.
Oh, sorry, I was muted.
Oh, no problem. Go ahead.
Yeah, so hi, I'm Jonghan, PhD student in the Professor Park's group. So during pick and placement process, the passive components may be misaligned systematically due to accuracy of placement, and it may give rise to leaf flow failure, such as skewing, overhanging, or tilting. So these kind of leaf flow failures induce a different variation of solid joint shape, and they could severely affect to determine the fatigue life of solid joint. So in this study, we compared the fatigue life under various misplacement, components length and width direction from 0 to 100 micrometers, step of 25 micrometer. And the surface evolver is used to obtain the realistic solid joint shape of various components overlaying cases, and the cross-sectional samples are compared to validate the shape. Then it is imported into ANSYS to calculate the life. The thermal cycling condition is -55 to 125 Celsius and 40 minutes per cycling. For the X overhanging cases, less fatigue life is used for the total fatigue life, since the left and the right solid joint are different. For Y overhanging, fatigue life of severe overhanging is decreased to 14.8%, and the severe misaligned case in X-axis would reduce 42.8% of total fatigue life to compare with zero placement offset, because the solder length rapidly decreased when the component is shifted to right further or next direction. So therefore, the passive components overhanging in y-axis has better fatigue life rather than on x-axis. This is what I did for this work.
Great, thank you very much, Zhang Wong. Our next speaker is Banan Garakani, a PhD student in his 4th year. And are you a 4th year PhD student, Banan?
5th year. I mean,
5th year, okay.
Yeah. Thank you.
Go ahead.
I hope my video is on. Yeah.
I don't see your video, but
yeah, I don't know why.
Good.
Is okay. Okay. So thank you. So this is Banan Garakani. We are in a CAM that's part of IEC in Binghamton, and we're working mostly on a flexible and stretchable electronics for wearable applications. So in wearable applications, either the person wear it or run it, and so the interconnect typically are subjected to large amplitude of strain, and we know that most of these interconnect, even the stretchable one that is commercially available on the market, they cannot survive in like 10%, 20%, or more than 50%. So we need something that is reliable for tens of thousands of cycles, for let's say 50%, 100%, because it's for wearable applications. We, in collaboration with Liquid Wire, developed a metal gel that is kind of highly stretchable liquid metal, because when you say liquid metal, most of the people think about mercury. But this one is a gallium indium tin eutectic alloy of this one. So unlike mercury that's toxic, this one is not toxic and has a low vapor pressure. And by adding some proprietary additives, and also the gallium oxide that naturally formed once it's exposed to the air, we modify the rheology so that it can be stencil printed. So because stencil printing is a fast and established process, so it can be good to the manufacturing scale. So if you look at the graph that you can see, the comparing between the liquid metal and stretchable silver and carbon paste, you know what I'm saying now. Comparing to silver and carbon one, that none of them is going to survive more than 100%. Stretchable liquid metal conductor, even at 250% strain amplitude, the relative change in the resistance is just about, let's say, 10 times of the initial resistance. And so we don't see any hysteresis in a resistance versus strain. And the one that you see in the hysteresis is for the substrate. Substrate is a polymer, is a TPU, and that's normal. And one of the applications for this one is for foldable and stretchable transmission line in RF application. As you can see, for foldable and bendable transmission line, the signal line is a metal gel, and also the ground plane also is a copper. And for stretching, both of the ground and signal are actually liquid metal. And after subjecting to 100% for 1,000 cycle, S1, 2 parameter before and after are mostly the same. So no significant change after cycling at 100% for 1,000 cycle. Thank you all for your attention.
Banan, thank you very much. We have 2 more speakers. Our next speaker is Chungyang Kai, a 4th year PhD student defending next year at Binghamton University.
Thank you. Hi, everyone. My name is Chungyang, and the research topic I'm going to present today is about the study of electromigration reliability of 3 types of solder joints, which is lead-free eutectic tin bismuth and SAC305, and hybrid solder joint of tin bismuth and SAC305. So right now, the tin bismuth solder is attracting more attention because it has many unique advantages. The biggest advantage is that it has a much lower melting point, which requires much lower reflow peak temperature, which will reduce the reflow cost. And also it will provide a more better thermal cycling performance during the thermal cycling test. And so that's why we want to perform the studies of electromigration to see if it is also showing better performance than the SAX-305 when it comes to electromigration reliability. So we assemble 3 types of solder systems, which is homogeneous SAX-305 as control group and the homogeneous tin bismuth, and also the hybrid mixture of SAX-305 components and the tin bismuth paste. So we can provide insights for the different failure mechanisms. So until 500 hours, as you can see from the figure, in the first row is SAX-305. It still shows no failure with the proceeding of the electromigration. For the second row is the tin bismuth. You can see there's a void forming inside the solder joints, and the cracks will form at the anode, cathode side. And for the hybrid side, hybrid joints, it will also show failure, which is worse performance than the homogeneous SAX-305. So after performing the finite element analysis, we can see that the tin bismuth solder has some reduced current crowding effect, because the bismuth provides the smaller resistance. Yet the tin bismuth still fails earlier than the homogeneous SAX-305, which suggests that the intrinsic properties of the tin bismuth and the SAX-305 has some properties like activation energy difference during the electromigration test. So generally speaking, for recommendation of the packaging, so although the tin bismuth solder might provide a better fatigue life and a lower melting point, when it comes to high power electronics, when the electronic devices is under higher current stressing, we still need to pay attention if the tin bismuth will fail earlier. In one perspective, it is because of its faster diffusion process of activation energy. On the other hand, it's about the low melting point, which is more sensitive to the dual heating effect. Yeah, that's all. Thank you for listening.
Great, thank you very much, Zhang Yang. And our final speaker is Preeth Sivakumar, a PhD student in the final year at Binghamton University.
Thank you, James. So my research is mostly to study the tin whisker growth mitigation using conformal coating. So based on all my work, we have come up with some strategies for mitigating the tin whisker mitigation using the conformal coating. So what we did is first we evaluated some of the commercially available conformal coating, then tried to improve its adhesion and mechanical properties. And based on the results which we got, we tried to establish a relationship between the coating property and the whisker mitigation behavior. So this result or this relationship would help in developing new conformal coating in the future that can effectively mitigate a tin whisker during the long-term aging. So basically what we found out was the relationship between the strength, toughness, adhesion strength, and protection against the moisture absorption. All of them played a huge role in extending the time for the whisker to completely penetrate through the coating. So we evaluated the effectiveness of parylene, 2 different thicknesses, effectiveness of soft polyurethane, which is urethane, at multiple different thicknesses, and hard polyurethane with and without silicon rubber to see the effect of increase in toughness and also the increase in the adhesion strength. So based on the results which we saw, one, which when there is a conformal coating, the number of whisker activities on the tin surface reduced drastically. That was because the moisture to the tin surface is delayed, which means there is less stress in the tin layer, which means less delayed whisker formation. So within the conformal coating for parylene, increase in the thickness reduced the adhesion strength, which had a huge impact in the whisker activity. So reduction in adhesion strength for thicker parylene coating had an whisker formation at the earlier stage and penetration at slightly later stage. So in order to improve the parylene C coating, the adhesion strength of the parylene needs to be improved. And the soft polyurethane, because the material property itself is too soft. So which means the thickness of this coating needs to be increased in order to increase the time for the moisture to reach the thin layer. And also for a hard polyurethane, increase in the adhesion strength and also increase in the toughness of the coating resulted in delaying the whisker formation. So comparing all the conformal coatings, hard polyurethane with silane agent, which enhance the adhesion strength, and in the presence of silicon rubber, which enhance the toughness of the coating. So all of them combined together provided the best whisker mitigation behavior. So the future direction of this work is parylene coating. Because of the adhesion strength, the whisker mitigation is not that good. So we are going to try different silane agents in order to improve the adhesion strength of parylene C coating. And also the thickness of soft polyurethane is way too high, above 120 microns. So we are trying to add some of the hard filler materials to increase the strength and toughness of the coating, so that even with a thinner soft polyurethane coating, we can get better whisker mitigation behavior. Yeah, thank you.
Great, thank you. Thank you very much. I'd like to thank all the speakers again. I mean, it was really a challenge, and the students certainly rose to the occasion of really concisely sharing their research in a very concise manner. So kudos to the students for really kind of, upping their game and really showcasing the work that they're part of and the relevance to the iMAPS community.
Yeah, this is Dipak. I echo what James just said. I really would like to thank the students. You're working on such complex technical, challenges, and yet you're asked to present all that in 2 to 3 minutes. I think each one of you deserve big applause for bringing your work to us. Everyone excelled. Everyone got across their point very well in the time allotted. So I congratulate each and every one of you. And I also thank Benson Chen and Dr. Busnaina for accepting, our invitation to speak at this student event. And we are hoping that each one of you will join us for the symposium that's planned for next May in 2022. I'd like to see each one of you there and meet with you face to face. Wish you all the best in your career, students. Thank you.
Thanks again. I'm going to thank everybody for sharing with us. That was excellent, and I know it's a lot of work, and we appreciate it. And with that, I'm going to stop recording.